we are looking at the definite integral today as a limit. So on Friday, we're actually going to talk about the definite integral. Today, we're going to see like a glimpse of it. And I've been hinting at it when I've drawn like the integral and I put the numbers on it and I write f(x). So we have a hint at what a definite integral is. And a definite integral is, by definition, just the little integration symbol. The integration symbol itself means the word sum. So it kind of looks like an S. It stands for a sum. The word definite means that it has a beginning and an end. So we are only talking about integrals right now that have a beginning and an end. And that would make sense for talking about area under a curve, because you can't find the area of something that doesn't have a beginning or an end. So we are going to take this definite integral and we are going to relate it to a limit, and that limit is going to be related to our Riemann sum. So up to this point, every time we talk about Riemann sums, we've been talking about the fact that the more Riemann sums we have, the better. So what happens today is as we look at limits, instead of having a limited number of subintervals, the limit allows us to have an infinite number of rectangles. So that's why we bring a limit into a Riemann sum. So let's warm up with a multiple choice AP question that says the graph of the derivative is shown to the left. If f of 0 equals 0, so that means that the original function started at the origin and the derivative started at 1. Which of the following must be true? So the first one says that the original function f of 0 is greater than f of 1. Well, we know f of 0 is 0. If you look at the graph of the derivative, what do I know about f of 1? So if the derivative is at 0, what does that tell you about the original? It is a what? Potential strata. So then we also want to look at our derivative graph and look at what's happening to our derivative graph. So the derivative graph from 0 to 1 is decreasing and positive. So again, it all goes back to that chart So if f prime is positive, my original graph is doing what? If f prime is decreasing, my original graph is, yeah. So it's increasing though. That's the key piece of information, right? So if the original graph f of 0 started at 0, but the derivative tells us that it's increasing and concave down, and 1 is a potential extrema, is f of 1 going to be greater than or less than f of 0? Yeah. So f of 1 has to be bigger, which means it cannot be the letter f. So now anything that has Roman numeral 1 cannot be an answer. From 1 to 2, the derivative graph remains positive. So that means that x equals 1 is not an extrema. It is a false critical point because we did not change signs on the derivative. Therefore, this graph is going to continue to increase. What happens though is the graph changes from decreasing to increasing. Therefore, x equals 1 is a point of inflection. So my graph goes from concave down to concave up. And then at this point here, it actually is like another POI. So it goes from increase to decrease. So that means it goes back to concave down. And then at x equals 2, my graph's a little off. At x equals 2, we have a 0 and changing signs. So at x equals 2, I do have a match and it changes size. And so f of 2 is greater than f of 1. Well, yeah, because it's increasing from 0 to 2. So the only way for a graph to be smaller is if it's not increasing, but it is increasing, so this is true. So now it can't just be this one. And then we have f of 1 is greater than f of 3. Do we know anything about f of 1 and f of 3? Can I prove anything? So when it says which of the following must be true, does f of 1 have to be greater than f of 3? No. Alright. So those are just it's just kind of a little warm up. And it leads into talking about sigma notation and summation formulas. So a summation formula is that weird little E symbol. We had them back in the day. We talked about them in the past. Technically, every time you're doing an area under the curve, you're summing all of those rectangles together. So a Riemann sum is a summation. What we're going to do today is learn how to write a Riemann sum as a summation. So in order to be able to write something as a summation, I think it's important to know what a summation means. So the first couple examples, I'm really just teaching you the summation symbol. So we're kind of going backwards in time and saying, okay, what is a summation? What does it mean? So the n is our upper bound. The I is what we call the index, and it equals the lower bound. So when we write these limits, we're going to have k sub I or delta x sub I. That just stands for this starts at the lower limit value, but it's easier to write an I than it is like a number without that. So the first summation says that if you add up a constant from a through n, it's going to equal that constant times n. That should make sense. That is basically a Riemann sum, right? So it's the width of the rectangle times the height of the rectangle. The constant's the height of the rectangle. And then if you start getting into x squared, x cubed. Those are your summation formulas for each of those out into our universe. So again, constant x squared, x cubed. So if I ask you to find the summation from 1 to 6 of I, you're going to use that formula we just had. So the formula says that this is my n value. So in this case, the n value is 6. So it would be 6 times 6 plus 1 all over 2. So 6 plus 1 is 7. 6 times 7 is 42. 42 divided by 2 is 21. The old school, or like the original way, would say that you are adding all of the numbers from 1 to 6. So this is like the formula way. The original method said that you need to take 1, which is the starting number, plus 2, plus 3, plus 4, plus 5, plus 6, and add them all together. That is like the true summation. So it's a linear number being added together from 1 to 6. So it's all the numbers in between. And again, if you would add them, 11, 15, 18, 20, 21. The next one, if you had to do it without a calculator, you would, or by hand, you could use a calculator. Because when I tell you, those are going to be some large numbers once you're getting into like squaring 12 and then adding it to 11 squared, adding it to so on and so forth. I'm also going to show you how to get the summation on your calculator. So if you were doing it again the purple way by hand, this would mean you would start with 3 squared and then 4 squared, and we would add them all the way up until we got to 12 squared. So up like 9, 16, 25, all of those perfect squares up to 144. If you do it using your formula on here, then it is n, which is 12, times 13, and then 2 times 12 is 24. 24 plus 1 is 25. All over 6. So let's use our calculator and compare all of those answers. So let's do the first one where we add up all the perfect squares by hand. So 3 squared plus 4 squared plus 5 squared. 6 squared, 7 squared, 8 squared. And we got 645. And then you can try the formula.
45 when I added them up.
Alright, well now we're going to do the method on the calculator. So you're going to hit math. You're going to go down to number 0 for summation. And then you're going to type in J equals 3 to 12, and then make a J squared. And then example 2, evaluate the following summations. So again, it would be like that same idea. And if you were doing it by hand, you would have to use your two formulas and do subtraction. So that first formula is I squared. So it would be that n times n plus 1 times 2n plus 1 all over 6 minus the n formula, which is n times n plus 1 all over 2. So in this case it would be 10 times 11 over 2. Plus 4, so then that becomes 4n. And did we get 370? So again, how does that all go back to calculus, right? So it feels kind of like, that wasn't calc. So it all goes back to calculus by saying, okay, the integral from a to b is the same as the summation from I equals 1 to n. And then the delta x is going to be our n subintervals. So if you go back and you think about what we said delta x represented the other day, we said, okay, delta x is going to equal b minus a all over n. So that's not changing. That is still holding true. So that b minus a all over n isn't going anywhere. We're still using that, and we're going to use that in our summation limit for delta x sub I. So the delta x sub I is going to get replaced, God bless you, with that b minus a over n. So for example, b was 2 and a was 0. Then when we looked at our summation formula, this would be 2 over n. So the n is going to be part of my summation for my limit. So I tried to kind of type that out for you as step-by-step directions, but I think it's the first time you're looking at it, but that's a little confusing. So essentially that b minus a over n times I is going to happen inside my formula. Now, if we're doing left endpoints, it's more difficult because you have to add this I minus 1 inside your formula. If you're doing right endpoints, then it stays I. If you're doing just a Riemann sum and a limit, it stays I. So both of these represent my f of x's. And again, the width, or that delta x sub I, is going to be b minus a over n. So if you think about your integral, when I'm talking about this, it's f of x and delta x. So you're going to have this part of the formula in here that's happening right here. And then you're going to have this part that's happening at the end for my a and my b. And then that integral is going to change to the summation symbols. So the integral is going to change to the summation symbols. The f of x is going to change to a, which is where your integral starts, plus that delta x sub I subbed in, times that delta x sub I. So you are almost going to see like the same things twice. I promise once you see them, it like starts to make sense. So it says the limit process as a Riemann sum, right? So the limit as n approaches infinity, meaning now we have an infinite number of subintervals. So instead of telling you 5 subintervals, now it's an infinite number of subintervals, which means it is finding the area like your calculator did where it's shaded underneath. So it's the limit as n approaches infinity from I equals 1 to n for 1 plus 2I over n squared. So that means that this is an x squared function because it is the f stuff squared. So this is like my x. So this means f of x equals x squared. The 2 here and here tells me that b minus a has to equal 2. The number here is a. Remember, it's always a plus my width. So a is 1. So that Riemann sum gave me a bunch of key information to my original integral. So my integral starts at 1. My b minus a is 2. So that means that if a is 1, b minus 1 equals 2. So you add 1 to the other side, b must equal 6. My f of x is x squared. And when we write an integral, it has the differential dx because that stands for the width of the rectangle. So you just wrote your first integral from a Riemann sum. So the Riemann sum as an integral looks like that. There are like 2 multiple choice questions where you have to write the Riemann sum and integrals on a date. It's usually a limit to a sum to a limit. So otherwise I would just skip this. because it's not, it's confusing a little bit, but it helps, and sort of like the ebb and flow, it makes the connection. So, why, what, do, how. Let's look at another one. This is like the boom formula that you need to know. Conversion from one to the other and back. So if the integral from a to b of f of x dx looks like such, then it is the summation as n goes to infinity of f of x sub I delta x. And again, your delta x is b minus a, and your x sub I is a plus b minus a over n I. So which of the following limits is equal? So pull this right off an AP exam. A is 3, B is 5. So B minus A must be 5 minus 3, which is 2. So now I'm looking at all of those potential options, and the outside delta x has to have a 2 in it. So it cannot be A or C. Because I don't have 2 at the end. Like 1. And B minus A is 2. And then the next thing I like to look for is my A value. Because it's A plus delta x sub I. So now I need a 3 and a 2 in my problem. So 3, 3. So it's the difference. The difference is the 2 on the k. So again, your formula is a plus delta x. Delta x is b minus a. So 2 on B. Goodbye. That's all my answers. Other direction, going from a Riemann sum to an integral. So now I have the square root. So the square root is my function. The 1 is my a value. So if the 1 is my a value, all of my integrals that I'm going to select must have a upper or lower limit of 1, or neither. Doesn't matter. No. What do I need my lower limit to be? Yeah, so how many choices have a lower limit of 1? 1. So, again, I think it's very important to look for those key pieces of information. So, on the outside, again, we're here, we have my delta x, which is my b minus a. So, I needed the difference from b to a to b3. So, 4 to 1 is 3. A worksheet, and then a couple textbook problems. Is there answer? The front of the worksheet is the non-calculus, like summation stuff. The back is going between calculus and the Riemann sum. Tomorrow we'll do trapezoid. Mm-hmm.